Hello everyone, this is Xiaoran from WinLab, Rutgers University. Today I'm going to present our work towards flexible wireless charging for medical implants using distributed antenna system. This is a collaborative work between me and my colleagues from Microsoft, University of Science and Technology of China, Northwest University, University of Massachusetts Amherst, and Alibaba Group. Deep tissue wireless power transferring is crucial and sought after in many scenarios. For example, in-tissue wireless power could potentially help implant user avoiding surgeries for battery replacements. And the flexible in-body wireless power could greatly improve the versatility and even functionality of the controlled drug release. Further, the deep tissue wireless power is a key enabler for in-body and body area communication, such as transferring out monitored vital sign data or interfacing of electronics with the human brain. Existing approaches for in-body wireless power transferring are mainly two categories: near-field and mid to far-field wireless charging. Near-field method leverage the inductive coupling between transmitting and receiving cores. The power source could be either radio source or acoustic signals. But charging devices in this method have inherently large form factor due to their efficiency suffer greatly from the core size to distance ratio. As such, it can be bulky, inconvenient, and not easy to be placed within some small audience. Further, this charging performance will be greatly reduced because of the charging core might be displaced from the in-tissue blood flow. On the other hand, middle-field to far-field wireless charging method has relatively low charging efficiency due to its long charging distance and large tissue signal attenuation. Besides, it also possesses overheating issues due to its high operation frequencies. Our method belongs to this category, and we focus on solving these issues by leveraging the advantages of wireless beamforming. Beamforming greatly enhances the wireless charging efficiency by aligning the transmitter's phase towards the target receivers. In traditional energy beamforming systems, the centralized phase array would form an energy beam towards the energy receivers. As a result, any obstacles blocking on the beam path would largely reduce the charging efficiency, and the blocking subject herself will receive even higher energy than the intended target, hence suffering from overheating. By contrast, distributed beamforming spreads the energy transmitters around the target, but aligning the transmitter's phase at the target at the same time. As demonstrated in previous works, in distributed beamforming system, energy will be spatially focused around the target receiver as if forming an energy ball, which potentially avoids overheating and blocking issues, which further translates to a safer charging environment. It is hence a natural choice for our deep tissue charging system. Implement distributed beamforming is, however, much more difficult than traditional centralized beamforming, due to the fact that the transmitters are geometrically distributed, which means independent signal processing and inhomogeneous channel state information at each transmitters. Further, large signal attenuation in deep tissue makes obtaining CSI prohibited. We hence adopt a closed-loop implicit phase alignment method that requires no CSI, and all transmitters can work fully independent. Here's an example realization with 3 transmitters. In the beginning, each transmitter possesses random initial phase, and the receiver will send feedback as all the 3 transmitters perturbate their phase 3 times, which leads to 3 random RSS received at the receiver. And then the receiver will pick the highest RSS and tell the transmitters, you keep these phases and perturbate another 3 random phase perturbations. By doing this, the received signal strength will keep increasing at the receiver side until it converges to optimal. Here is an example realization of distributed beamforming in our real-world testbed. We can clearly see the convergence process while building up the beamforming energy, and we can consistently achieve nearly optimal received power using this method. Directly apply the previously mentioned distributed beamforming method is not going to work due to the unique requirements and challenges in our scenarios. The first challenge is that implanting devices are usually very low power. The previously mentioned method requires the receiver frequently compare the receiving signal strength and encoding a feedback signal to transmitters, which is power demanding in the long run. In our design, we offload all these computations to an out-of-body leader node using Backscatter. This is feasible because the previously mentioned beamforming method only requires RSS as a target receiver. Here's an example input and reflected signal from our backscatter. As can be seen, the reflected signal shares similar RSS as input signal, but in a different frequency band. As a result, we can infer the received signal strength as the implanted backscatter using the reflected signal received at an out-of-body leader node, and let the leader node undertake all the following signal processing and feedback broadcasting. As a result, we call our system in and out. However, typical passive backscatter have long linear input-output relationship due to their matching networks are designed to work optimally in low power. That means the output signal strength can decrease while the input signal strength increases, which would fail our previously mentioned beamforming algorithm. In our design, to solve this issue, we propose a dual antenna backscatter design to isolate the receiving and reflecting radio chains. This will lead to a monotonic input and output signal strength relationship, as can be seen here. We next see a demonstration realization of our prototype backscatter. In this experiment, we program a USRP to broadcast a changing 950 MHz narrowband signal, and we use a spectrum analyzer to receive both this 950 MHz signal and the reflected 935 MHz signal. We can clearly see this monotonic relationship between the reflected signal and the 950 MHz input signal. The next immediate challenge is the severe energy loss in animal tissues. Due to the two-way backscatter signal propagating, there will be less than -100 dBm received signal strength at the out-of-body leader node, which translates to no CSI or even RSS available for beamforming. In our design, we adopt chirp spreading to extract the minor signal variations under the noise floor. So here is an example showcase of chirp spreading signal. We let the transmitter broadcast a series of amplitude increasing chirp signals and put our backscatter in a 10 cm pork belly. As can be seen here, the received signal at the out-of-body leader node is under the noise floor, whereas the chirp are still visible in the spectrum. However, modulating the chirp signal at our carrier frequency requires tight synchronization. The example here shows small timing offset between two chirps leads to unstable received signal, which could cancel the realization of our beamforming algorithm again. As such, we propose a two-step chirp synchronization method implemented before the beamforming realization. The first step is to compensate the carrier frequency offsets use standard CFO compensation method, but there will be residual timing offsets after this step. So for the second step, an observation here is that larger ISS fluctuation rate reflects larger timing offset between the two chirps. We hence use the fluctuation rate as a feedback to minimize the residual offsets. So after the carrier chirps are synchronized, to infer the signal strength change at the backscatter, we propose a decoding matrix similar as LoRa decoding. We call it as PCSS0, denoted as the peak of frequency domain correlation between the received backscatter signal and the local reference chirp. We proved the linear relationship of PCSS0 and the received signal strength at backscatter in our paper. Here is an example of decoded PCSS0 for an intentionally increasing input signal. We can clearly see the increasing trend of the PCSS0 here. And here is the time domain and PCSS0 domain at the out-of-body leader node in this example. As can be seen, the time domain signal is fully under the noise floor, but we can still clearly decipher the increasing signal trend in the PCSS0 domain. We can hence use this PCSS0 as an RSS indicator to fit in our previously mentioned beamforming algorithm. Last but not least, our system leads to bootstrap the backscatter. The embodied device might not necessarily have power at the first place. It's a chicken and egg problem. In our design, we naturally choose the leader nodes as an anchor. Keep in mind, to avoid over-the-air signal attenuation, the leader node is an out-of-body node but placed near the implanted device. We therefore beamforming at the leader node first and artificially introduces phase noise to disturb the beamforming. Here we can see the results of artificial phase tethering. The energy ball is enlarged artificially. We are hoping the spread side lobe could hit the backscatter and wake it up by keep working on this phase tethering process. The next random phase perturbation again changed the energy distribution, but also missed the heating. So we keep working on this perturbation. And finally, the backscatter will be hit and awakened by the consistent phase perturbation. Note, this cold start is a natural process by our default system design. We bootstrap the system as long as the leader node observes the first PCSS0 in the 935 MHz backscatter channel. We also provided optimal phase perturbation choices analysis in our paper. After solving all the beforementioned major challenges, we can finally put together an in and out system. We prototype our system using 21 software-defined radius and conduct extensive experiments using 2 types of animal tissues, including pork belly and turkeys. Here, you can see we use a mobile node serve as a leader radio. We next demonstrate some of our experiment results. So here is a high-level experiment result for our overall system. We measured the energy distribution inside of 4 slices of pork belly. We can clearly see an energy hotspot tightly formed around the target implants. And we delivered 372 microwatts of RF power using our large 20 by 20 meter testbed. Please note our system could achieve much higher delivered power in a real regular living room because they are usually smaller than our testbeds. And our system also has less safety constraints than traditional beamforming method because of the advantages in distributed beamforming, as we discussed previously. Next, we evaluate our system using micro-benchmark. We first evaluate the chirp synchronization accuracies. We can see the residual time offset is minimized after the second step of chirp synchronization procedure. And because of the chirp synchronization method is an iterative procedure by itself, so it takes time to converge and finish. So here we evaluate the time consumption of this process. As can be seen here, the time delay is quasi-linear to the number of transmitters, but this procedure only needs to be done once. We also evaluated the cold start successful rates and time delays versus the number of transmitters, and we present the result here. As can be seen here, the cold start method has relatively high successful rates with a short bootstrap time when there are more than 8 transmitters. Please keep in mind the leader node is placed 1 meter away from the implanted backscatter. We also evaluated the cold start success rate and time delay versus the leader to backscatter distance, LB distance in short. So here we vary this LB distance and see the change of the success rate and time delays. As can be seen here, the cold start method performs reasonably well when this LB distance is less than 1 meter. So in real-world in and out implementation, this leader node can be a smartwatch or cell phone, which is reasonably close to this implant. Keep in mind, we fix the number of transmitters to be 10 transmitters here. And next, we evaluate the beamforming establishing time consumptions versus the number of transmitters, which is the slaves here. Because this beamforming process is also an iterative process, as we discussed before. So we evaluate this matrix here. As can be seen here, this beamforming establishing time is fast, which means less than 0.4 seconds when there are 24 transmitters. And also this time consumption is quite linear to this number of transmitters. We also evaluated the beamforming performance versus the backscatter orientation. We use the power percentage represents the beamforming performance, which denotes as the actual received power versus the theoretical optimal power in percentage. As can be seen here, when we rotate this backscatter, the delivery power is insensitive to the rotation of the backscatter, which we believe is a big advantage for implant users because she can then move around. Keep in mind, this is and natural advantages comes from the distributed beamforming system. Next, we conduct field study for our in and out system. We first evaluate the beamforming performance in various medium. So here we evaluate the power percentage and the time delay versus 4 different mediums: air, water, pork, and turkey. As can be seen here, our beamforming success consistently in various wave propagation mediums, which is in 10 cm deep. In the next field study experiment, we compare the beamforming performances of our system versus a state-of-the-art system, IVN, in stationary case. IVN is a multi-frequency, multi-antenna blind beamforming design, which means the received signal strength in IVN system will be changed over time, whereas the received signal strength will stay relatively constant in our system. As can be seen, the result is presented here. The more transmitters we have, the higher power gain we can achieve compared with IVN. Our system delivers around 18 times of power than IVN when there are 24 transmitters. Next, we study the beamforming performances of our system versus IVN in mobile case. We put the backscatter inside of a turkey and mount this turkey on the robot. And we then program this robot, let it move in a different speed. The result is shown here. As can be seen, our system outperforms IVN by around 7 times in relative slow speed. We believe these experiments are important because the implants might move slowly with the in-body blood flow. Let's take a closer look at the distribution of RSS for IVN and our system when the robot moves in slow speed. The results is shown here. It can be seen the lowest RSS received by our system is 0.053, whereas 90% of the RSS in IVN is less than 0.029, which means our system delivers higher and more stable energy than IVN. To conclude, here are 3 major contributions of our work. Our work is the first far-field distributed beamforming-based wireless power transferring system that charges deep tissue implants at a near optimal power level. And our system involves several technical innovations, including Backscatter leader-slave 3-party beamforming without explicit CSI measurements, and the 2-phase leader-slave chirp synchronization algorithm, and also the radio co-starts through intentionally imperfect phase alignment. And also, we prototype our system on software-defined radios with the monotonic backscatter PCB design, and we conducted comprehensive evaluations of the system. We also plan to pursue subsequent clinic experiments for further validations.